As already mentioned, we will be talking about the Arm System Trace Macrocell and how we can use it to instrument the bootloaders of a complex SoC. First, we will briefly talk about what the System Trace Macrocell is. Then we will take a look at how to instrument a bootloader by modifying its source files. Once we will have the instrumentation ready, we will configure the trace analyzer in winIDEA to record and display STM messages properly, and we will see how we can use instrumentation and winIDEA for boot up timing analysis. So let's say that we have a big multi-core SoC that's running a complex configuration like AUTOSAR Classic and AUTOSAR Adaptive on the same SoC, and we may even be using some trust zone features like OptiOS. Well, the more complicated our system is, the more complicated the boot up process becomes, and we may very well end up in a situation where the boot up process has gotten so complex that it takes a significant amount of time to get the system up and running. At best, this makes for a bad user experience, and at worst, this can even be a safety issue. In any case, it is a real possibility that when we develop such complex systems, we may have to analyze why the boot up is taking so long and optimize the system or fix potential issues that cause timeouts and so on. And this is where using instrumentation and trace with iSystem tools can prove useful. We can perform this timing analysis using various trace technologies, but in my opinion, Arm System Trace Macrocell, or STM, is very well suited for this purpose. It is easy to configure, it adds very minimal overhead, and it offers a very convenient way to instrument the application to provide trace data with timestamps. It works by injecting data into the trace stream, and this data can then be captured through the trace interface using a tool such as the iSystem IC5700. This data comes over the AXI bus, or the APB bus in the case of the basic stimulus port, and a timestamp is added before it is output through the trace interface. Usually, all cores in an SoC have access to the STM stimulus ports. As you can see on this diagram, data writes over the AXI bus to the STM peripheral get merged with the rest of the trace data from ETM and other trace peripherals, and output through the trace interface. So, in effect, what all of this means is that the STM stimulus ports are memory mapped as registers, and the application can perform data writes to an STM channel, and any data that's written to this address appears in the trace stream. These addresses are 64-bit aligned and are separated into the basic stimulus port and the extended stimulus port. The basic stimulus port has 32 STM channels, and the extended stimulus port has over 65,000 of them. All of this information with more details is also nicely described in an upcoming application note written by my colleague, so keep an eye on our website for that if you want more details on how STM works. But in essence, from a programmer's point of view, all you need to know is that if you write to a specific register, this data will appear in the trace stream. I will be demonstrating how STM can be used for boot up timing analysis by instrumenting the bootloaders of a Renesas R-Car H3 SoC, although this example would apply without modification to the R-Car H3 as well. These SoCs contain a Cortex R7 core and several Cortex-A 53 and 57 cores. Usually the R7 is used as a boot core, and then the bootloaders follow the ARM Trusted Firmware model, so they are separated into several stages. On the left, you can see a fairly basic example of a system that's running AUTOSAR Classic on the R7 core and AUTOSAR Adaptive on the A53 core. And you can see that the boot up process is already quite complex. Now, on the right, you can see a diagram of a system that is also running the secure OptiOS in addition to the two AUTOSAR systems. And you can see that the bootloader configuration becomes really quite complex. Now, despite this complexity, all of these bootloaders, with the exception of the boot ROM, can be instrumented using STM and traced at the same time. Later on in the example, we will see how winIDEA shows us a nice overview in the timeline of what is going on. Now, I think the best way to demonstrate exactly how STM functions from a user's perspective is to actually show you an example of instrumentation. So we will try to instrument the BL2 bootloader with just a minimal example of instrumentation, something like 1 or 2 functions, so that you get an idea of how this is achieved. We will be instrumenting the code by sending values over STM at function entries and exits. At the function entry, we will be sending a unique function ID for each function, and at the function exit, we will be sending a 0. From the order and timing that these values are received by the profiler, it can then calculate how the functions are nested and what their execution time is, and so on. Now let's actually dive into it. So here I am in a Ubuntu virtual machine, and I have the R-Car Yocto sources downloaded and the Bitbake environment initialized. I have already run DevTool to create a working copy of the sources. I'm not going to cover the specifics of how Yocto works right now, but if you have questions on how Yocto and Bitbake work and how to modify sources and create patches, I have written a technical note on that topic that we can send to you. So I have pre-prepared this workspace to save some time. I have 2 terminals open, and I am located in the source directory for ARM Trusted Firmware, which is the Yocto recipe that contains the bootloaders. First, let's go into the include common folder, and we will create 2 header files here. The reason for this will become apparent later on when we will be configuring the trace analyzer in winIDEA. First, I will create a file called something descriptive like STM instrumentation values bl2.h. Here we will define the values that will be sent over STM. For now, we will leave this file empty, and we will fill in the necessary information once we actually start instrumenting the code. Next, I will create a file called STM Instrumentation Macros.h, and this is where we will actually create the macros that will be used to write to the STM registers. So I will open the file, and the first thing that we will define here is the base address of the STM stimulus port. We will be using the basic stimulus port for this demonstration, and this is the only SoC specific part of this demonstration. So in my case, on the R-Car M3, the STM base address is E900 and then 0010. This 10 at the end is technically not part of the base address. It's just an offset so that we write into the correct field of the STM channel registers. But I felt it's less confusing if I just put it as part of the base address, so don't worry too much about this 10 at the end. Next, I will create a macro that will handle the offsets needed to write to specific STM channels. So if you recall, we have 32 channels on the basic stimulus port, and they are spaced 256 bytes apart. So we need to offset each channel by 100 hex. So I will define a macro STM DTS, which will take a channel number as a parameter, and this will be an integer write to an address that's determined by the STM address and the channel offset that's calculated by this channel number multiplied by 256. Now we can use this macro to write to a specific STM channel. We could stop here, but I'm going to define 2 more macros to make our lives easier. We are going to be instrumenting the function entries and exits, so we can define a macro for each case. First, I will create a macro for the function entry. I'm going to call it STM trace bl2 entry, and it's going to take a value parameter that will contain the number that will be output via STM. So this number will tell the trace analyzer which function is currently executing. So basically a function ID that we will define for each individual function. This macro will write to the STM channel, let's say 7. So when we will call this macro with a value specific to a function, the value will be written to the STM channel 7. Now we will create a similar macro for the function exit. So I can just duplicate this line and call it STM trace BL2 exit. The main difference here is that all function exits will be indicated by a 0 sent over STM. So this macro does not need to take any parameters. And the value written to the STM channel 7 will be 0. That's all we need for this file, so I can save it and exit. Now we will actually instrument the code. So I will go to the other terminal window and navigate to the BL2 folder of ARM Trusted Firmware in the work directory. And I will open the BL2 main.c file. First, we can add the two header files that we created. So that would be STM instrumentation macros.h and the currently empty file STM instrumentation values bl2.h. I will open the instrumentation values file in the other terminal so that we can enter new values here when we instrument a function. So, as already mentioned, we need to instrument the function entry and the function exit. This bl2 main.c file only contains one function, and we will start by instrumenting the function entry. This is relatively simple. We just add the macro that we wrote earlier to the beginning of the function. So that would be STM trace bl2 entry, and we can write something descriptive for the value, like STM BL2 main. This value is not yet defined, so we can define it here in the instrumentation values file. Let's write STM BL2 main and assign it a unique value. 0 is already used for indicating a function exit, so the next best choice is 1. So that's it for the function entry. Now let's tackle the function exit. Let's scroll down to the end of the BL2 main function. And there's a bit of a catch here. It may be tempting to just treat this curly bracket here as the function exit point, but that may not necessarily be the case. The function can have multiple return paths, in which case you would have to instrument all of them. Or the function can branch off to somewhere and never actually return, which is especially common in bootloaders. In my case, I know for a fact that this run next image function call is executed, but that function never actually returns. In fact, all it does is branch off to some other bootloader stage. So this BL2 main function never actually gets past this run next image function call. So this is the actual exit point of this particular function, and we should put the STM instrumentation just before this function call. So let's just quickly do that. I'll write STM trace BL2 exit, and we don't need to provide an argument because all we're sending is a 0. There really isn't one correct way to approach this function exit problem. You just have to kind of figure out each individual challenge and put your engineering skills to use when determining where to instrument function exits. You can also use winIDEA to step through the code and find function exits that way. In any case, the nice thing is that if you do mess up and a function exits before the instrumentation instruction is executed, this will show up nicely in the Trace Analyzer timeline, because at some point in the timeline, the function will start, and then you will have one continuous infinite line, which will make it pretty obvious that from the Trace Analyzer's point of view, the function never exited. So there's probably something wrong with the instrumentation. Anyways, we're now done with the instrumentation of BL2 main. So let's just do one more function. And let's choose a subroutine of BL2 main. So for example, this BL2 load images. Let's save this file and exit to the terminal. And let's open BL2 load images.c. Again, we have to include the two header files. So let's just quickly do that. Now we can scroll down to find the load images function. Here we go. And we can instrument the function entry just as we did before. So let's write STM trace BL2 entry, and let's come up with a descriptive name for this function like STM BL2 load images. This value is not yet defined, so let's define it in the instrumentation values file. And let's assign it a unique number. I think 2 is a good candidate. Now let's tackle the function exit again. And thankfully, this function has a nice and obvious return statement. So our job is a bit easier this time. So let's add the instrumentation macro just before the return statement. And that should be it. Let's save these files. And now we have instrumented two functions in the BL2 bootloader. And we are ready to test if our instrumentation worked. At this point, I would tell you to rebuild the bootloaders and flash your board. And of course, you would need to do that, but thankfully I have already prepared this example earlier, because compiling anything in Yocto takes a long time. So my board is already flashed with this instrumented version of the BL2 bootloader. And we can now switch to winIDEA and configure the Trace Analyzer to capture and display these messages. Here we are in a winIDEA workspace, and I have already configured it so that I'm able to attach to my target. Now we will need to configure the analyzer to be able to capture and analyze the STM data that the bootloader is now generating. I have the analyzer window open, and I will create a new configuration by clicking on this hammer icon. I will name it STMBL2. Here we will uncheck coverage and enable manual configuration. Now we can click on OK, and we will enter this manual configuration dialog. And the tab we're interested in is this STM tab on the right. We want to use STM, so we will click on Enable. And we're not done just yet. Down here, we need to change the port enable mask. And we don't really care about masking at this point, so we can just enable everything by writing FFFFFFFF. Now we just need to check this timestamps checkbox, and we are good to go as far as STM configuration in general is concerned. So we can click OK. Now that we have configured that, STM data will be captured by winIDEA, but now we want to display this data in a nice way. And for that, we have to make winIDEA understand what this data coming over STM represents. So we have to make the analyzer aware of the STM channel and the function values that will be sent over that channel. There are two ways we can do this. One is by writing an XML file that enables some really powerful and complex configuration options, but is also quite complicated to write. And another way is by using a quick and simple menu in our graphical interface, which is quite a bit more limited in terms of configuration options, but it contains just enough functionality that it covers this use case of bootloader instrumentation perfectly. So I will show you how to configure this via the graphical interface way. And if you're interested in the XML option, the application note that I already mentioned also contains information about this XML configuration, so look forward to that. Let's open the Profiler tab, and we will first uncheck code and enable data profiling. This is a peculiarity of this graphical interface configuration of STM. Now, don't get me wrong, we will still be doing code profiling, but we will be configuring it via the data profiling menu. So down here in data areas, we will create a new trace configuration. We will give it a suitable description like BL2. And then in this dropdown where it says location, we will choose STM. Now we have to enter the STM channel number here. If you recall, we are sending data over the STM channel 7, so let's enter that here. Now the profiler knows where to look for this data, but we need to tell it how to interpret the data. Down here in the value area, we will choose an interpretation method for the data, and we will choose function entry exit. Now the profiler will know that the values it's getting are function IDs, but we still need a way to assign a sensible name to a function ID, and this is where the two header files that we wrote earlier come into play. We could have just written everything into one header file, but because we put instrumentation values into a separate file, winIDEA can parse that file and get information about which ID corresponds with which function name that we came up with. So in this dropdown, we will select a define file, and we can browse for our STM instrumentation values bl2.h file that we wrote. If we quickly take a look at this file, we can see that we wrote some very descriptive names for the two functions, and the profiler will use these names in the timeline display. So this is everything that we needed to configure for this example. And now we are ready to do a trace recording and actually see what we have achieved with all this. First, I will reset the CPU so that we start from the beginning of the boot process. Now I will start the trace recording, and I will run the CPU for a little bit. This is enough, so let's stop the CPU. And the trace recording is also automatically stopped. Here we can see now that we recorded something, and if we zoom a bit better, we can see the two functions that we instrumented in the profiler timeline. You can immediately see that this load images function is a subroutine of BL2 main, because when load images is executing, it's dark red, indicating that it's currently executing, and BL2 main is light red, which means that it's currently waiting for a subroutine to return. And this is all there is to it. We have successfully instrumented our bootloader, and we can see our results here in the profiler timeline. Of course, this is just a minimal example. We only instrumented two functions. So let's take a look at what a more complete instrumentation would look like. Here I have a trace recording that's been created earlier, and it shows the entire R7 IPL, the BL2 bootloader, and U-boot. And this is just so that you get an idea of what is possible with this approach. So, in conclusion, we looked at the basics of Arm System Trace Macrocell. We instrumented a small part of a bootloader, and we looked at how to configure the winIDEA Trace Analyzer to capture and display this instrumentation. If you want to use this approach for boot up timing analysis, you should now be able to replicate this example by following the steps that I took. And although I provided just a minimal example, it is easily scalable to cover the entire boot up process. This concludes the presentation part of this webinar, so I would like to thank you for your attention.
So thank you, Otton, for this good insight how to profile a bootloader. There were some questions coming in, and some interesting one I will simply ask you. Number one is, Is it necessary to have a trace interface like HSSTP available on the ECU, or is it also possible to store the STM trace data on chip in some sort of buffer?
Yes, so HSSTP is obviously ideal, but without it, the STM trace messages can be stored in the ETB, so the embedded trace buffer, or they can be stored in RAM, and the ETR can be used, so the embedded trace router. But the storage in that case is, in both of these cases, is rather limited. So this approach could probably work for something like bootloader instrumentation, but for something like complex OS profiling and stuff like that, it's probably insufficient. Depends on the use case. But in any case, even with this approach, reading the data out via a regular JTAG interface, a winIDEA trace license is also required.
Thank you. Question number 2. Can multiple cores write to the STM at the same time?
Yes, absolutely. But they should each write to their own channel or set of channels. So the user should configure a separate channel array, or different cores to different channels, and yeah.
Okay. Number 3, what is the maximum trace recording time?
Again, depending on which approach is used, if we have HSSTP available, then the number of messages coming over STM is so small that we can record practically infinitely. But in the case of ETB, it depends on the amount of storage available. It's still longer. I mean, the STM messages don't really take up much space because we only instrument function entries and exits. So it is probably completely sufficient for a bootloader, but yeah, it depends on the use case.
Okay, thank you. One more. Is it possible to program the instrumented bootloaders with winIDEA, or do I need another programming tool?
Yeah, I didn't show it in the presentation, but that's exactly how I programmed my board with winIDEA. We support QSPI, HyperFlash, and eMMC devices. So yes, absolutely.
Okay, thank you. Otton, thanks for the presentation. Thanks for the answering. We are now finishing. All other questions are answered later by email. We are now coming to the end of the webinar, and I would give you some additional information. So don't forget to download the presentation in the handout tab of the menu. Our knowledge base support.isystem.com contains always the newest published content. If you want to receive webinar invitations, please register to the iSystem newsletter or check the Meet Us page for upcoming webinars. If questions may arise in the future, please feel free to send an email to webinar@isystem.com, or of course, reach out to your contact person at iSystem. So for the moment, we have a summer break regarding webinars in our time zone. So the next webinar is planned for September, and the subject is most probably about debug and trace on Cortex-M devices. Thank you for joining, and please fill in the feedback form after leaving. All the best and goodbye.
Goodbye.